I'm delighted to be here. When I was in graduate school, I started doing work in mid-infrared astronomy because no one really had done work in that or much work in that area before, particularly from the ground for the ground-based telescope. And I went into it because it was exciting and it was new, and who knew what you were going to find. So the allure of mystery attracted me to this wavelength range that I'm still working in. So I want to talk to you about the landscape of mid and far IR data and observatories. I'm going to cover just most recent, project a bit to the future, and I want to emphasize that this wavelength range really is still very untapped. There's a lot you can do that's new, and a lot we can learn about the universe at this wavelength range. Um, First, I want to start um, the discussion with the importance of this infrared to astronomical studies in general. So this is a spectral energy distribution of a star-forming galaxy, and you can see two bumps, one in the optical with in the UV with the stars, and you go to the infrared, and you see all the emission from the interstellar medium. And the interstellar medium is, of course, key to understanding the origins of stars, planets, and galaxies. And you can see that much of the radiation from the galaxies and other objects come out at these wavelength range. And so they're very key to understanding the universe and astrophysics. You can see a number of important line diagnostics that I'm sure the speakers will touch on. And down below, we show the context for SOFIA and why it's important. We have the transparency of the atmosphere, and you can see that SOFIA's transmission is much higher because it gets above the water vapor, for example, in comparison to ALMA, which is on the ground. All right. So this is a timeline of recent, present, and future mid-IR facilities. And it shows starting in 2000 with Spitzer, and of course there were things that predated that. But it's amazing that the field is, less than 100 years old, which is why it's so ripe for discovery still. And then going on into the future. So let's just touch upon, I'm going to give you in some sense a personal tour of these observatories because I've worked with each of them scientifically, and they all had breakthrough discoveries. So here's Spitzer. Spitzer had a prime mission of 2003 to 2009, went for 3.6 to 160 microns. So again, there's an overlap with what SOFIA does. And then it had a really long extended warm mission at the shortest wavelengths. Now, I think when this happened, I was a professor at Illinois, but then I transitioned actually to Space Telescope at some point there. But what I did with Spitzer was this Spitzer survey of the Large Magellanic Cloud, surveying the agents of galaxy evolution. And we did a large imaging study of the whole galaxy using the IRAC and MIPS cameras. And then we actually followed up with a spectroscopic survey to understand the nature of the point sources we were finding. And so this image here actually shows you what the emphasis was, which we were studying dust evolution in galaxies. And dust is actually important at the key transition points where material starts in the interstellar medium. That's what you're seeing here in green with the 8 micron band, which had the CC stretch of PAHs. And then you have IRAC, which is shown in blue, which is the stars, actually mainly. Oh, somebody maybe needs to mute. I think it's Suhail needs to mute. Suhali? Okay. And blue is the old stellar population, and those are the stars that are producing dust, returning it to the interstellar medium. And then MIPS in red are really the hot spots where you have massive star formation. And of course, you're creating stars, but you're also consuming the dust if you looked at it purely from a dust evolution cycle. And then following on closely on the heels of Spitzer, we had the Herschel Space Observatory. So this is phenomenal. We just had Spitzer that brought us to 160 microns, and then Herschel overlapped with Spitzer at starting at 55 microns, going 100 to 672 microns. And for me, again, I did surveys of the Magellanic Clouds. We did both the LMC and the SMC. And this we called the Herschel inventory of the agents of galaxy evolution or heritage. And here you're looking more in that peak of the SED. You're looking at the dust emission. And so this is dominated by the interstellar medium dust. This is actually a combination of some of the Spitzer bands with the Herschel bands. And the color gradients you're seeing here actually have to do a lot with the temperature of the dust in this galaxy. And we were able to actually map out the dust. And there's a paper which is mapping the dust to gas mass ratio and showing that it varies in the galaxy. It's not constant. Gas to dust ratios aren't constant. So that was very illuminating. All right, and now let's come to SOFIA. I'm here now. I do have a paper out with SOFIA. But what I'm going to talk to you about now is the opportunity that you have with SOFIA that you're going to learn a little bit about today. It's, of course, started main operations in 2014. So it's again on the tails of Herschel. You can do follow-up on those things. And it's designed for a 20-year lifetime. And it covers a wide range of wavelengths. Here we have 0.4 to 612 because we have an optical guide camera that's sometimes used for occultations, but in general, it's that wavelength range that Ariel discussed with 5 to 600 microns. So this shows you in a very pictorial sense the importance of SOFIA in what it can offer. So this is the radiation from the sky and things that hit the ground, the rays that hit the ground, are windows that are very transparent, the optical, some near UV, and then you have the submillimeter and radio wavelength ranges. And of course, you can get above it all by going to space. And there's a lot of advantages to space, but it's a lot of work to get to space. Here's the far infrared wavelength range, 25 to 350 microns, that really is very inaccessible from the ground. You have to get very high up. But here is where SOFIA flies. So SOFIA flies 99.99% of the water vapor. And so you can get above a lot of the issues that you can't get transmission through, mostly water. And you can see the sky and do lots of really cool observations. And the other point is that SOFIA is the only far infrared, so this is going to the longest wavelengths beyond 30 microns. It's the only far infrared observatory for this next decade. And SOFIA will help prepare you all for both scientifically and technologically for the Astro 2020's ambitious future. You are the people who are going to take advantage of that future. And far infrared's part of that. So SOFIA advances Astro 2020 science by directly addressing one half of the decadal science priorities. So with SOFIA, you can actually pursue a lot of the things. And the three themes they point out: cosmic ecosystems, worlds and suns in context, new messengers, and new physics. And you can exploit the opportunity SOFIA provides to get training, to learn about instrumentation, and you will be defining and developing these future far infrared observatories that they describe in the report. So we've created a science traceability matrix to show how SOFIA science actually traces and maps directly onto the decadal. This is a public, and there's a link down here. It's a bit of an eye chart. I'm just going to touch on what is in the traceability matrix. So we have the decadal science question, key measurements, SOFIA instruments, SOFIA observations. And we have published papers out on most of these. And of course, there's lots of room through proposal applications to learn more about them. And just to give one example, how do star-forming structures arise from, interact with the diffuse interstellar medium? key lines to understand this are like the C2 and the 0163 micron lines. They arise in the interface from where stars' energies come in and the molecular clouds that may or may not be destroyed by these stars. We can also look at light hydrides, kinematics, and far infrared polarization. And you can see at the third column the SOFIA instruments that can be used to address these questions. And then last but not least, what we've highlighted here are some of the legacy programs. So these are data that are collecting data, goes immediately into the archive, and it's accessible to you immediately to do archival work. And we have special archival calls that you can use to support yourselves while you're mining this data. We of course do a lot of work in the cosmic ecosystems, which involves stars and particularly the interstellar medium. A growing area is this worlds and suns in context, which relates to the NASA S&P question, are we alone? And we have one legacy program where we're mapping water on the surface of the moon, but there are a lot of interesting solar system observations as well as nearby star-forming regions. And then last but not least, the theme of new messengers and new physics. How does the universe work? This is in the area of time domain. Now, time domain astronomy in the far and mid-infrared is very new. We haven't really had facilities to develop it. And you have an opportunity to actually develop and create this field of what happens, what varies in the far infrared. There are some observations exhibiting accretion from massive young stellar objects. And there are also supernovae. All right, SOFIA's efficiency and science productivity are on the right trajectory for SOFIA to achieve its full scientific potential. Its annual publication rates have doubled over the past 3 years on topics ranging from the Earth to high Z galaxies. And this link on this page brings you to this brochure shown on the right, SOFIA Science, Remarkable Results. And this shows some of the highlights. Most of them are from the last 2 years. Legacy science programs that I had mentioned in that table are 30% of the SOFIA schedule. And again, they are there to enrich the archive, to have breakthrough discoveries, and we'll hope that you will use them. All right, a little bit more about SOFIA, its capabilities, and how they'll complement things. We have 5 scientific instruments in this wavelength range, and then of course there's the focal plane imager. There's Forecast, which is the faint object infrared camera for the SOFIA. Its wavelengths are 5 to 40 microns, and there's a GRISM. That's what's used in the lunar mapping of the moon, water on the moon. There's EXIS, which is the shell cross-shell spectrometer, and it's 4.5 to 28.3 microns. It has an extremely high spectral resolution, 1000 to 10 to the 5. There's HAWK Plus, which is the longest wavelength camera of 50 to 240 microns, and it has the polarimeter. This is what you can measure magnetic fields with. There's FIFI LS, the far infrared imaging line spectrometer. It's long wavelength as well, 51 to 203 microns, and 600 to 2000 spectral resolution. And then there's GREAT, the German receiver for astronomy at terahertz frequency, 63 to 612 microns. It's a heterodyne spectrometer at very high spectral resolution, comparable to what you have at ALMA. Now, this plot here shows how the SOFIA instruments are complementary to JWST and ALMA instruments, and you can use them in unison to learn a lot, to have a multi-wavelength tackle on these problems. At the shortest wavelengths that overlap with JWST, you can see that the EXIS spectrometer has much higher spectral resolution than does JWST, and the GRISM Forecast is in between. Of course, in the far infrared, there's no other observatory at the moment except for SOFIA, so you would get your far infrared bolometry or polarimetry. You would get FIFI-LS spectroscopy at medium resolution, or if you need really high spectral resolution, which is important for ISM studies, you would use GREAT. Likewise, the range over what you get. First of all, compared to JWST, again, the Hawk Plus instrument for imaging goes to longer wavelengths. So if you need a far infrared data point, you come and use Hawk Plus. If you are looking at the same wavelength range at JVST, it really depends on the brightness of your target. So forecasts can observe extremely bright targets, massive young stellar objects in the galaxies, the galactic center, the moon. There's lots of things that forecasts has and can still tackle. And then you have JVST, and this is just showing the upper range of what JVST can tackle. So they're very complementary to each other. Likewise, on the spectral line sensitivity, again, this is showing this with respect to wavelength. In the far infrared, the SOFIA spectrometers are what you need to use to do any measurement in the far infrared, particularly of these key lines of oxygen and carbon. And then when it comes to the shortest wavelengths, it depends again on your target brightness, but then also spectral resolution. So up on the top here is XEs are 50,000, and what we show here on the bottom is what the upper reaches of JVST is when it's unsaturated in normal mode, not subarray. It's fun to take SOFIA observations. SOFIA is a crewed mission. There's a lot of emphasis on safety during flying, particularly during COVID. You can see on the right, this is a picture taken of the crew doing observations of Venus. You can see everyone's masked, socially distanced. There's very clear and tight protocols. This team is amazing. They're heroic. They're very dedicated. During the 2021, they did flights from Palmdale. They did a deployment in Cologne, Germany. They did a deployment in French Polynesia. And if you get time on SOFIA, and as things open up, we are inviting investigators to come fly and be there when we're taking your data. And even if you aren't flying with us, you can follow it as it flies. So typically SOFIA flies 4 times a week, Monday to Thursday, and you can follow it as it flies on any flight trackers. Mine's favorite's FlightAware, and you just type in NASA 747. Now, one of the advantages of SOFIA, because it safely returns to Earth every day, it's a very reliable platform, is that you can improve and upgrade and even replace with new instruments on the back end of SOFIA. And by doing so, you can increase the capability by up to a factor of 10 in better sensitivity and mapping speed with the new instrument. I'm not going to go into too much detail here. There's a link below with the full report. But we are on the road already with the first step, which is to upgrade the Hawk Plus instrument with improved detectors that will increase mapping speed by up to a factor of 4. It's in a formulation phase right now, and we will have an evaluation this summer. After that, and then that is expected to be delivered in 2024. After that, there's an anticipation to look for a new instrument. And all these decisions are science-driven. What's the most important science that the community wanted? And the community said, well, we'd like two. Now, we could only proceed with one in the US. And it could be either a direct detection spectrometer with high spectral resolution or a terahertz mapper. And that the direct detection spectrometer improves SOFIA's spectral line sensitivity by a factor of 10 with improved detectors and the high spectral resolution. And terahertz mapper is basically using great, but filling the focal plane so you can map things much faster by a factor of 13. And that second instrument would be delivered in 2027 and then be available for science. And then a possible third instrument would be considered, but the landscape that you all will be shaping will change what the science needs are. And so there will be another check-in with the community before that's done. All right, so just very quickly, James Webb launched. I hope you all got to see it. It's very exciting. It goes from 0.6 to 228 microns. I talked about the upper range, but of course, JWST discovery space is immense because it goes very faint. This is the photometric performance, and of course, the spectroscopic performance is phenomenal. So take advantage of that opportunity along with SOFIA. There are these 4 instruments, NearSpec, NearCam, NEARIS, and MIRI. I am involved with it because actually I became a member of the JWST MIRI science team, and I encourage you all, when you see opportunities to join science teams or to be involved with future endeavors, even though it's not there now, it is an exciting thing you can help shape, and look for those opportunities. A lot of my programs are focused on extragalactic star formation at low metallicity. I am, of course, revisiting the things in the Magellanic Clouds and focusing on this new, very hot infrared object in the N79 region that is located in the N79 South Cloud. And it's an object we found with Herschel and Spitzer, H72.97 minus 6939. It may be a superstar cluster under formation because it's extraordinarily luminous. All right, and just touching on what is in your future that you will be helping shape, utilizing the training you're getting with SOFIA and James Webb are these far infrared probe and origins. So the decadal talks about the importance of having either a far infrared or X-ray probe, having a probe line, and they called out far infrared or X-ray for this next, for the first probe. There are, and I encourage you to pay attention to what's happening there. There are a number of what I call pop-up workshops this spring to understand and define what these are. The IR STIG is having one in person in Boulder, Colorado, March 30th through April 1st. And there is a far infrared science development workshop just the week prior, March 21st to March 23rd, that will have a virtual and in-person component. And then, of course, in the far future, what the decadal asked for is a line, another line of great observatories. They're starting off with the UV optical observatory, but they do call on for something like the Origin Space Telescope study, which I co-led. It's a very exciting mission. Again, will have a huge amount of discovery space over what you will get with SOFIA or an IR probe. If it's even close to what we envision, it'd be 1,000 times more sensitive than anything before. JWST size mirror and 3 orders of magnitude of wavelength coverage, very comparable to SOFIA. So take SOFIA, make it bigger, put it into space, cool the telescope. That's a key point. And you would have origins. So until then, we have SOFIA. This is your observatory to learn and do and explore and help define the future. And I'm happy to answer any questions you may have.
Thank you, Margaret. I don't see any questions right now, but I did have one. Well, it's for an invitation. So after this school, some people will be excited about studying SOFIA data or getting new data. What are the opportunities open right now, as of today?
Right. So with SOFIA, as I'm hoping a number of you actually put in applications for our time. That the deadline was last January 28th. But even if you didn't, we have a very rich archive. And there you can just start playing with the data right now. We will have an archival funding call. It'll be later this spring, so stay tuned for that. And that's to get funding. And if you're a student or a postdoc, please do consider submitting. Our last archival call, we had a number of early career scientists get awards. I think it's a great opportunity or entry point to work with SOFIA data.